Alright, good morning class. It is Mr. Manta here, and we're going to be kicking off our lesson number 13. Today should be Tuesday, March 24th, I believe, and we, as a class, are on lesson 13. Hopefully you've been sticking with us, talking all about color reflection today. That might sound like nonsense right now, but in just a second we're going to find out exactly what it means for color to be reflected. Before we jump into today's new material, as usual, we're going to kind of review the stuff that we talked about yesterday. Now, yesterday's video got very long. I don't know, like 36 minutes. That's longer than I meant for it to be, but we were trying to capture this really big idea that there's different kinds of light that are not visible. Hopefully today's video will be shorter. I've tried to make the slides shorter. We'll see how it all turns out. But yesterday's video, the whole point of the idea was capturing this idea that when we think about all the different colors of light that make up the rainbow, that's really only a tiny fraction of all the light that there is. When we say that like red has the longest wavelength of all the different colors of light, that's kind of true, but it's not exactly true because there is light that has a longer wavelength than red. It's just that we can't see it. We call that light either infrared or radio. Radio waves have the very longest wavelengths of all. Infrared has a little bit longer than red. When we say that violet light has the shortest wavelength of all, again, it's true, but not totally true. It has the shortest wavelength of all the colors that we can see in the visible spectrum, but it doesn't have as short of a wavelength as ultraviolet light, and X-rays are even shorter than that, and gamma rays are even shorter than that. We just can't see those other kinds of light with our naked eyes. Again, the colors of the rainbow are the visible light spectrum, or the visible colors, and everything else outside of it are what we call non-visible light. And there's a whole bunch more non-visible light than visible light. With that in mind, we're going to knock out today's do now. All right, you should be answering these questions just in your notebook. You're going to jot down a 1, 2, 3, as well as there's going to be, okay, you should jot down the numbers 1 through 9 in order to give me your answers. Here are the questions 1 through 3. Pause the video and write just the answers in your notebook now. And bringing it back, those are the first 3 questions for our do now, and these will be the remaining 6 questions for our do now. It's a matching section. Pause the video, answer these questions in your notebook now. Alright, and we are bringing it back. We're going to run through the answers for today's do now. First of all, we have numbers 1, 2, and 3. Number 1 is asking us the color of a light wave is determined by its, we should know this because we've talked about it a lot, wavelength. If you said wavelength, then give yourself a star. That is correct. Number 2 says the energy of a light wave is determined by its, and actually again, the answer is wavelength. So if you said wavelength for 2, go ahead and give yourself a star. We learned that wavelength determines both color and the amount of energy light has. Specifically, the longer a wavelength is, the less energy light has, and the shorter it is, the more energy light has. So violet has more energy than red. Question 3 is asking which diagram below shows the way that colors of light combine. The correct answer here would be diagram A. I know that that's the correct answer because when I combine all 3 colors in the middle, I end up with white, or white light. And we learned a couple days ago that white light is what we see when we have all the other colors mixed together. Diagram B over here is instead showing you the way that colors of paint combine. And when you mix all the colors together, you instead get black or brown paint in the middle. For the remaining questions, this matching section about non-visible light, you should be able to know, you shouldn't understand enough about all these different kinds of light that you can answer these questions. So questions like these could show up on a quiz or a test. Number 4, this kind of light has the longest wavelengths of all. That was C, radio waves. Number 5, this kind of light can pass through your skin and muscles, but not your bones, is D, X-rays. Number 6, this kind of light is seen by thermal cameras. That one might be tricky to remember. That is going to be B, infrared light. Infrared light is all about heat. So thermal cameras that see heat can see infrared light. Number 7, this kind of light gives some people sunburns. That is going to be A, ultraviolet light up here. Sunscreen is made to block ultraviolet light so you don't get a sunburn. Number 8, this is the kind of light that you can see, we call that E, visible light. And lastly, number 9, this kind of light is made by a nuclear bomb. That's the really dangerous kind we talked about, F, gamma rays. All in all, we had 9 questions on the do now. Hopefully you got 9 out of 9. If not, it might give you an indication of what kind of stuff you should start reviewing. All right, jumping to some new material for today. We're going to start today with a focus question. Now, We've already learned in our lessons why red light looks red and blue light looks blue. It's because of their wavelengths. We saw a few days ago that if you line up 4 different lasers of different colors and you shoot them, you'll see that a red laser produces red light with these long sloping wavelengths, whereas a violet laser produces violet light with these really short, tight little wavelengths. So we know why red looks red and why blue looks blue and yellow looks yellow and violet looks violet, because of the wavelengths. But today's focus question is, so then, why is a red balloon red? Why is a blue balloon blue? When we look at objects instead of light or laser beams, where does that color come from? Now, you might be asking, maybe it's their wavelength. Maybe a red balloon has a red wavelength and a blue balloon has a blue wavelength, but that wouldn't make sense because a wavelength is something that light has. It's not something that an object like a balloon has. So you can't say that a red balloon has a red wavelength. It's a balloon. It doesn't have a wavelength. It doesn't make any sense. Some of you, I know, because I've spent enough time with you in class, might give me an answer like, oh, well, a red balloon has red paint on it, or a blue balloon has blue paint on it. And I mean, that kind of answers the question, but it doesn't really answer the question, because we could just turn the question into like, well, then why is red paint red, and why is blue paint blue? And just keep on moving the question down along the road. The question still remains, where do objects get their colors from? Why are red objects red? Why are blue objects blue? They don't have a wavelength like light does, so where does that color come from? Well, to try to answer this question, first of all, I'm going to have you make a prediction. Pause the video and just as soon as I say so, and give me, this is going to be classwork question 1 in the classwork form. You're going to be making a prediction. Here's the question right here. Read it, pause the video, and answer classwork question 1 now. And bringing it back, I'm very curious to see what people's predictions ended up being. We're going to jump in today and kind of start answering this question of why are different things different colors by watching a video. This is from National Geographic, a scientist going around to a carnival and messing with some laser beams. And he's going to see if he can pop balloons using a very powerful laser. Watch closely.
Putting more objects in the line of fire, but this time at the local arcade. I rounded up some young hotshots to show them the awesome power of the laser. This laser is 10 times stronger than the one found in a Blu-ray player, and I've brought along a few props to show its true power. First up is laser pointing at popcorn kernels, all right? And I'm focusing it right on the popcorn. Now watch this. There it is.
No way.
Awesome. Have you ever seen that before?
That's crazy.
Pop the kernel, right? That's the heat from the laser.
What?
Next one, right? Let's turn it onto the
okay.
matches. Now watch this one. It's right on the head of the match, right on the tip. Thank you very much.
Did that just
Thank you very
happen?
much.
Wow.
How was that? Okay, now that you've seen that, I'm going to point it at the balloons, right? Once at the red, once at the blue. What's going to happen to the balloons?
They're gonna pop.
They're going to pop.
I think I'm gonna pop too.
They're going to pop.
Yeah, it popped the popcorn, it burned the match. It's definitely gonna pop the balloon.
So we've seen that light emitted from a laser can be transformed into a weapon of destruction. But what will happen if it hits the balloons? Will it pop both balloons, pop only the red balloon, pop only the blue balloon, or pop neither balloon? Let's go red balloon first, all right? Red balloon.
Uh-huh.
Yeah.
Right. So far you guys are all right, okay?
Okay.
Right, now how's about the blue one?
Uh-huh.
What's
Blue one's
happen?
gonna pop as well.
Same thing's gonna happen?
In serio?
The fact that you're asking makes me feel like maybe there's something to this.
So the answer is B. It popped only the red balloon. Anyone any idea why? This is amazing. You can leave it on there pretty much all day long.
Because what do you put inside of it?
Nope.
It's not blowing up as much as the red one.
No.
Because it's blue?
Because it's blue. When we see an object as a certain
All
color,
right, now he's about to give you the answer. I'm going to give the answer, though, in a little bit more of a, hopefully a clear way. I'm going to jump in right here, and we'll see exactly why the blue balloon didn't pop at the end of today's lesson. This is an excellent way to introduce the big idea for today that can help us understand why the red balloon popped and the blue balloon
because
didn't.
only that.
Why couldn't the blue laser pop the blue balloon? Well, the answer is a little bit complicated. Today's big idea is this. When an object is a certain color, it means that it reflects light waves of that same color and absorbs light waves of all the other colors. When an object is a certain color, like a red balloon, it means that it reflects light waves. So a red balloon reflects red light waves of that same color and absorbs light waves of all the other colors. So a red balloon absorbs all the other colors of light. If that doesn't make sense, these pictures should make it make a whole bunch more sense. So here's what we're going to be looking at today. In this case, we have an object. We have a bright red apple, right? And this apple is sitting out in the sunlight, and we know that the sun produces white light which has all of the different colors within it, because that's how white light works. It's being hit with red light, and with orange light, and yellow, and green, and blue, and purple light, all at the same time. The thing that makes this apple red is that when all those different colors of light hit it, only the red light reflects. The red light bounces off. When the red light bounces off and you have someone like this guy over here standing looking at the apple, this red light is picked up by his eyes. I mean, maybe this guy doesn't have eyes right now. We'll give him some eyes. He sees the red light coming off of this apple being reflected, and it makes him think, he makes him see that the apple is in fact red, because it's emitting, but really it's just reflecting all of this red light. All the other colors of light that are hitting it, like the yellow and the orange and the blue, they're getting absorbed. They just they go in, you could say that they're getting converted into thermal energy. They're being absorbed by the apple, and they're not being reflected back out. So the apple doesn't look yellow, it doesn't look orange, it doesn't look blue. It looks red because it's reflecting red light. If that's still confusing, we'll see a few more examples of this. Here we have a green leaf. It's being hit with white light that contains all of the different colors, but most of the colors are being absorbed, except that green light right here is bouncing off of the leaf, is being reflected. When someone looks at the leaf, what they're seeing is all this green light coming into their eyes, and so the leaf looks green. All the other colors except for green are being absorbed into the leaf. We have another example. This time we have a blue surface, or some kind of blue object. In this case, when it is hit with all of the different colors that are in white light, it is only blue light that is reflected. And if you had a person over here, they would see the blue light coming into their eyes, and to them, they would see this object as blue. Because like a blue laser emits blue light, blue objects reflect blue light. It's only blue light that's bouncing off of them to go be seen by people. Hopefully you've picked up the pattern. We have a green object reflecting green light, a red object reflecting red light, and a blue object reflecting blue light. Each time all the other colors are being absorbed. So here's classwork question 2. You should answer this in the Google form, the classwork Google form attached to this. Tommy shines a flashlight, which has white light, at a green apple. Which colors of light will be reflected and which will be absorbed? We see all these different wavelengths of light going into the apple. What light is going to be reflected and what light is going to be absorbed? Pause the video, answer that question now. And bringing the video back, I'm going to go ahead and show you guys the answer. In this case, since we have a green apple, it means that green light gets reflected, bounces right back off the apple, whereas all the other colors, like red, yellow, orange, blue, and violet, are being absorbed. The apple is green, and so it reflects green light. If the apple was red, it would reflect red light. Now, while we're understanding this whole idea that the color that something is tells you what color light it reflects, we should also know something that makes it a little bit more complicated, which is that the colors black and white are special. They're a little bit different than the colors in the rainbow. So what you're seeing so far right here is just what we've been talking about the whole time. A red object, when hit with all the colors in white light, reflects red light. A green object reflects green light. A blue object reflects blue light. Well, if we also included a black or a white object on this diagram right here, here's what you would see. A white object, when hit with white light, reflects all of the colors of light. So you have red, green, and blue light coming in, and you have red, green, and blue light bouncing back out. White objects reflect everything and absorb nothing. Black objects are the opposite. When we have white light with all these different colors hitting a black object, it absorbs everything and nothing at all comes bouncing back out. That's why you don't see any light bouncing off of the black object. And it looks black because there's no light coming from it, so it looks like it's dark. White objects reflect everything and absorb nothing. Black objects reflect nothing and absorb everything instead. This is another example of it. We have a white object being hit with all the colors of the rainbow, and it's reflecting all of them. We have a black object being hit with all the colors of the rainbow, and it's absorbing everything. There's nothing bouncing back off of it. So it looks like it's just black or it's dark because there's no light coming off of it. Now, this can help you understand if someone's ever given you advice to, like, if you're going outside to play during the summertime and they say, you know, wear a white t-shirt because it'll help you stay cooler, you won't be so hot. Well, this explains why. If you have a white t-shirt and a black t-shirt and they're out there in the summertime and the sun is shining light down on these t-shirts, well, if you're wearing the black t-shirt, we just learned that black light absorbs all of the light that it gets hit with. So when the sunlight shines on the black light, it absorbs all that light, it converts it to thermal energy, and the temperature of the shirt goes way, way, way up because it's absorbing all that light energy and turning into thermal energy. When it shines down on the white t-shirt, though, we learned that white surfaces reflect everything. So all of the light just bounces right back off of a white t-shirt, almost like it's a mirror. And the white t-shirt doesn't heat up the way that the black t-shirt does. That's why you can stay cooler in the summer by wearing the color white. Now, since we've learned all of this today, we can finally tie back to our original question that we started with. Why is a red balloon red and a blue balloon blue? Well, you can shine white light at both of these balloons, and that white light will include all the different colors within it, because white light is what you get when you combine everything else. And if you do that, the red balloon will reflect red light, and the blue balloon will reflect blue light. That's what makes an object the color that it is. It depends on what colors of light it reflects. A red balloon is red because it reflects only red light. A blue balloon is blue because it reflects only blue light. This also can explain what we just saw in the video. Well, why didn't the blue laser pop the blue balloon? Well, he shot it with a blue laser. So we have a blue laser coming in, right? And we know that this blue balloon, it reflects blue light. If you shot it with a blue laser, but a blue balloon reflects all blue light, well, that laser just came in and bounced right back off. It couldn't be absorbed by the balloon. It couldn't be turned into heat, and it was the heat, the conversion into that thermal energy that was melting the other balloons. That blue light was getting bounced off, so it couldn't do anything to the balloon. It couldn't pop it. Knowing what we've also learned, we can make a prediction, hopefully, for this video. I want you to make a prediction just in your head. You don't have to write this down anywhere. I'm going to play this video quickly as well to round us out. What you're going to see is that there's a scientist who has a green laser. He's going to shine that green laser at 3 different balloons. One balloon is green, one balloon is green, one balloon is black. Here, I'll see if I can get it back up again. One balloon is green, one balloon is black, and one balloon is white. Try to predict which balloons will pop and which ones won't pop. If he shines that same laser at the green balloon, the black balloon, and the white balloon, and we know that a green balloon reflects green light, a black balloon will absorb everything, and a white balloon will reflect everything. Pause for a second, predict in your head which balloons will pop and which ones won't. I'll play the video now. Alright, so first up is going to be the green balloon. Shine a green laser at a green balloon, nothing happens. All that green light is being reflected because a green balloon reflects green light. You shine a green laser at a black balloon, pop! It popped right away because a black balloon absorbs everything. If you shine a green laser at a white balloon, nothing happens because a white balloon reflects all colors of light. Hopefully your predictions matched what actually happened here. It's all about what colors of light something absorbs versus reflects. Oh. Alright, and ladies and gentlemen, that is all that we got for today. That is your cue to go ahead and work on your exit ticket. It is exit ticket time. I want to point out that yes, there is independent work today. There's a short video for you to watch with some questions to answer about it. And I also want to mention today's cool thing. Again, this is just a bonus if you're bored and you want to check something out. Is this paint called Vanta Black. It is like the blackest black paint you could ever imagine. The picture that you're looking at here is this guy holding, I think, a basketball that's been painted with this Vanta Black paint. And it almost looks like someone just like put a black spot on top of the picture because the color, like the paint is so dark black that it reflects absolutely no light at all. Go ahead and Google the word or search on YouTube the word Vanta Black for some more information. But do that only after you've completed your exit ticket, your independent work for today. Alright, hope you guys enjoyed that lesson. I'm pretty sure it ended up being quite a bit shorter than our last one. And have a good day, and we'll talk to you tomorrow. So long.